59 earthquakes. One stretch of fault, 6 days. And the strangest part isn't the count, or the fact that this patch of ground is now shaking almost 7 times faster than it normally does. The strangest part is where it's happening. Because this exact segment of the San Andreas is the one piece of that fault that scientists have spent decades insisting cannot produce a major earthquake at all. It's the safe part, the harmless part. The section every prediction about California's future has quietly relied on staying quiet. And then, 4 years ago, someone drilled a hole 3 kilometers straight down into this fault, pulled out 4 meters of rock, and found something that should not have been there. By the end of this video, you'll understand exactly what that rock revealed and why it changes the story we've all been told about the big one. If you find yourself thinking differently about the ground under California by the end of this, do me a favor and subscribe, because this is the kind of thing we dig into here. Let's start with what's actually happening right now, because the facts matter more than the fear. Since Friday, one small stretch of the San Andreas Fault in central California has been producing earthquakes almost without pause. The center of it sits beneath Pinnacles National Park in San Benito County. It began with a pair of magnitude 3.2 quakes, struck a little over an hour apart, and then it simply didn't stop. It ran through the weekend. It picked up steam into the new week, and by the time you count them all up, the catalog holds around 59 located earthquakes in 6 days, right there in one tight box on the map. Now here's the honest part, and I want you to hold both halves of it in your head at the same time. Nobody has been hurt, nothing has been damaged. No agency has issued a warning, an advisory, or an alert of any kind. And on the raw numbers, none of that is surprising, because these are small earthquakes. The biggest one in the whole sequence would rattle a few dishes in the nearest town and go completely unnoticed in San Jose. So on the surface, this is a nothing event, a busy week on a busy fault. What makes it worth 20 minutes of your time is not the size, it's the location, because this swarm is sitting directly on top of what geologists call the creeping section of the San Andreas. And that word, creeping, is the entire key to the story. Most of the San Andreas behaves the way you probably imagine a fault behaves. The two sides lock together. They grind against each other and refuse to budge. Strain builds up in the rock, year after year, decade after decade, like a spring being wound tighter and tighter until one day it snaps, and all that stored energy is released at once in a violent earthquake. That's the locked fault. That's the machine that produces the big one. But this stretch, roughly 150 kilometers of fault running through central California, doesn't do that. Here, and pretty much only here, the two plates slide past each other continuously. They don't stick, they don't wind up, they just move, quietly, a little, every single day, at almost exactly the pace the plate boundary demands. And because it's constantly releasing its energy in tiny increments, the thinking has always been that it never gets the chance to store up the massive amount of strain a great earthquake needs. That single idea is load-bearing for everything you've ever heard about California earthquakes. It's the reason the standard answer to the question, could the entire San Andreas rupture all at once, has always been no. The creeping section was treated as a permanent firewall, a stretch of fault so slippery, so incapable of holding energy, that if a massive rupture came tearing down from the north, or up from the south, it would slam into this section and die right here. Every scenario where the big one is limited to just one half of California, north or south, but never both, rests on the belief that this middle section will always stop it. And that belief held for a very long time. So hold that question in your mind, because we're going to come back to it. Is this section really a wall, or does it just look like one right now? First, let me be precise about what happened this week, because the details turn out to matter. In the early hours of the morning, the sequence produced its largest event, a magnitude 3.94, just a few kilometers from Pinnacles, at a depth of around 4.5 kilometers. And this wasn't some rough automatic estimate that might get revised tomorrow. Dozens of seismograph stations recorded it. The epicenter was well surrounded by those instruments, and the location was tightly pinned down. In other words, this is a reviewed, well-constrained answer. The fault did exactly this, exactly here. Within minutes, 3 more quakes followed close behind, and the sequence kept ticking along for the rest of the day. Here's the first thing that's genuinely strange about it. It got bigger as it went along. Think about a normal earthquake sequence. Usually you get a main shock first, the big one, and then everything after it, the aftershocks, is smaller and less frequent as the fault settles back down. That's the pattern we expect, but this sequence did the opposite. It opened with modest quakes, ran for 4 days, and then produced its largest event near the end. That's backwards. And that backwards shape has a name. It's the signature of a swarm, a sequence driven not by one patch of fault breaking and its neighborhood adjusting, but by something progressively loading the fault, pushing on it over a period of days. Keep that word in mind. Something loading the fault. We'll get to what that something might be. Now, Central California shakes all the time, so before you can say 5 days of earthquakes means anything, you have to know what a normal week even looks like. in that same spot. And the researchers can tell you because they've counted. Over the first 7+ months of the year, that same box on the map produced a little over 300 located earthquakes. That works out to roughly 1.5 per day. That's the baseline. That's just Pinnacles being Pinnacles. This swarm produced 59 in 6 days. That's nearly 10 a day. The fault is running at somewhere around 7 times its own normal background rate. And that's not a statistical trick that vanishes if you draw the box a little differently. It's a large, clean, sustained change in how this specific piece of the San Andreas is behaving, stretched across the better part of a week. And here's a detail most coverage skips entirely. That number, 59, is not really a measurement of everything that happened. It's a floor. A huge number of tiny earthquakes get recorded on instruments and never officially published, because there are thresholds for size and quality, and analysts only review a portion of them. So whatever this swarm actually did down there, it almost certainly did more of it than the published count shows. The real number is higher. We just can't see all of it. The second strange thing is the shape of it in space. If one stuck patch of fault had simply broken and then adjusted, you'd expect a tight little ball of earthquakes clustered around a single point. That's not what we see here. Instead, the activity spreads out into a few separate clusters strung along tens of kilometers of the fault, sitting at different depths, active on overlapping but not identical days. That kind of distribution is far more consistent with something moving along the fault than with one spot failing in place. And the depths tell the same story. Some of these quakes are extremely shallow, right up near the surface. And that matters, because the shallow upper part of this fault is exactly the part that's supposed to be sliding freely, the part that's not supposed to be able to store strain at all. Yet the largest earthquake of the whole sequence started a few kilometers down and the activity reached almost to the surface. The fault is behaving in this 1 week in a way that doesn't quite match the simple picture of a section that just creeps and never bites. To understand why any of this is more than a curiosity, you need one number, and it's the number the entire safe reputation of this fault is built on. Over geological time, the San Andreas needs to slip at about 34 millimeters a year. That's the demand set by the movement of the plates, and it's about as solid a figure as this science produces. Now, the creeping section right here is measured to be sliding at roughly 25 to 30 millimeters a year, continuously right now. Look at those two numbers side by side. They're almost the same. And that near matches the whole argument. The difference between what the plate demands and what the fault actually slips is the amount of strain that gets banked in the rock, saved up, waiting. And a great earthquake is what spends that savings. But here, on the creeping section, that difference is close to zero. There's almost no strain being banked. There's essentially nothing to spend. The one arithmetic comparison, the plate rate versus the observed creep rate, is the entire scientific basis for calling this segment safe. And I want to be fair, it is not a weak argument. It's a genuinely good one. Scientists went looking for evidence of past great earthquakes here. They dug trenches across the fault, searching for ruptures that had broken the surface, and in the last 2,000 years they found none. The case seemed closed, until somebody looked in a place a trench could never reach. But before we go down that hole in the ground, I want you to see what this fault has already done at this exact spot, because it's one of the most spectacular pieces of evidence in all of North American geology, and it's sitting right underneath the swarm. Those dramatic rock spires that make Pinnacles National Park worth visiting, they're the eroded remains of an ancient volcanic field. And here's the astonishing part. They're only half of it. The other half sits near Lancaster in Southern California, on the far side of the fault, called the Neenach Formation. These two rock formations were once a single volcanic field, one volcano in one place. The San Andreas cut it in two and then carried the halves apart. Today they sit about 195 miles apart. That's roughly 314 kilometers of separation, accumulated over something like 23 million years. This fault didn't just crack the ground. That discovery is one of the foundational proofs that the Earth's crust really does slide sideways on this enormous scale. And the piece of that fault, sitting under Pinnacles, has been chewing through moderate earthquakes on a roughly generational schedule for as long as we've been watching. Magnitude 4s and low 5s showing up every couple of decades. By that record, a magnitude 3.94 here is completely unremarkable. It's normal. It's what this patch does. So here's where I want to pause and ask you something, because we're at the pivot point of the whole story. Given everything I've said so far, the tiny quakes, the near zero strain, the trenches that found nothing, this swarm should be nothing. So what would it take to convince you that the safe part of the San Andreas isn't safe after all? Drop your answer in the comments before I tell you what the rock said, because I'm genuinely curious where you land. Now here's the part that doesn't fit. At Parkfield, at the southern end of this creeping section, there's a hole in the ground more than 3 kilometers deep, drilled directly into the San Andreas fault itself. It's called the San Andreas Fault Observatory at depth, and it was built to answer a simple radical question. What is an active fault actually made of? A few years ago, a research team led by a scientist named Genevieve Coffey published a study in the journal Geology based on cores of rock pulled from that borehole. They focused on a band of badly mangled rock, just 4 meters of it, deep down in the fault zone. And the method they used is the beautiful part. When a fault slips in an earthquake, the friction along the sliding surface spikes the temperature by hundreds of degrees, just for an instant. That burst of heat permanently, chemically alters certain organic compounds in the surrounding rock. It leaves a fingerprint. And by measuring how far that chemistry has been pushed, you can work backwards and estimate how much the fault moved, and therefore, roughly how big the earthquake was. It's like reading the scorch marks a fault leaves on itself. Those 4 meters of rock contained the fingerprints of more than 100 earthquakes. And in most of them, the fault had moved by more than 1.5 meters in a single event. A slip of that size corresponds to an earthquake of at least magnitude 6.9. That's Loma Prieta in 1989. That's the scale of Northridge in 1994. And the authors noted that many of them could have been even larger because the technique for turning slip into magnitude is still being refined. A second dating method, using how the same frictional heat resets a radiometric clock in the rock, suggested some of these events happened within the last few million years, and Coffey has said publicly that some could have been as recent as a few hundred to a few thousand years ago. More than 100 major earthquakes, preserved in 4 meters of rock, on the one segment of the San Andreas that is not supposed to be able to produce a single one. Now, this is exactly the point where the story gets contested, and I want to give you both sides, honestly, because the version of this that goes viral online is not what the scientists actually said. Coffey's own framing is careful. Her point is that this means the central section can produce larger earthquakes than we thought, and we should be aware of that potential, that it's not always just gentle, continuous creep. A seismologist at the U.S. Geological Survey, Morgan Page, who works on the official California Hazard Assessment, put it plainly: the creeping section is a very hard place to study this way because the constant creeping erases the surface evidence a trench would look for, which is exactly why nobody had found these events before. And she acknowledged the consequence. If a large earthquake really can tear through the creeping section, then it becomes possible, in her words remote, for a rupture to start at the southern tip of the San Andreas, run through the middle, and continue all the way to the north. That scenario, the whole fault going at once, is exactly what people mean when they say the big one. But then there's the counterweight, the part the viral version leaves out completely. Another leading scientist who has worked at the drill site, William Ellsworth of Stanford, makes a narrower and more important point. He doesn't dispute the fingerprints in the rock. He says most earthquake scientists think these events happen rarely because tectonic strain is not accumulating at significant rates along this segment right now, if at all. Read that carefully because it's the crux of the whole thing. A fault that's releasing its strain by creeping is not, at this moment, banking the strain a great earthquake would need to spend. What the rock core's record is what this fault has done across vast stretches of geological time, under conditions nobody can fully reconstruct. It is not what the fault is doing this month. And that disposes of the scary claim floating around alongside this swarm, the idea that a magnitude 3.94 at Pinnacles means the big one is coming. It does not. A moderate quake in a shallow swarm on a creeping fault does not measurably change the odds of a great California earthquake. One of the study's own co-authors said it directly. People should not be alarmed. Building codes in California are good, and work like this exists precisely so we can figure out the worst possible case and prepare for it. Both things are true at the same time. This swarm is almost certainly nothing, and the fault it's happening on is not the fault we thought it was. To see why that second half matters in the real world, follow the creeping section southeast to where it ends, at Parkfield. It's a town of about 18 people, and it's arguably the most heavily instrumented patch of ground on the planet, because it sits right at the handoff, the exact point where the creeping section gives way to the locked San Andreas. And it produced one of the most famous experiments in the history of seismology. For over a century, Parkfield generated moderate earthquakes on what looked like a schedule, roughly every couple of decades. It was so regular that in the 1980s, scientists formally predicted the next one would arrive before 1993. They wired the whole area with instruments, and they waited. It didn't come in 1993. It came in 2004, more than a decade late, and when it finally ruptured, it broke in the opposite direction from the events before it. That failed prediction is one of the most useful things that ever happened to this field because it killed the comforting idea that faults keep appointments. And it's the reason the borehole exists at all. If you can't predict an earthquake by watching a fault from the surface, then the next question becomes, what is the fault physically made of? So they drilled straight into it, and they pulled out rock carrying the record of 100 ruptures nobody knew about. And there's one more reason Parkfield matters to this swarm. When the middle of a creeping segment slips, it transfers a little bit of stress to the ends of that segment. The northern end is near where the great 1906 San Francisco rupture stopped. I want to be completely precise here. That effect is tiny. It happens continuously, swarm or no swarm. And no responsible reading of this data turns this week's quakes into a trigger for anything. But the mechanism is real, and it's the honest answer to why anyone should care about a magnitude of 3.94 at all. And that brings us to the inversion at the very heart of this story, the thing I most want you to walk away with. While Pinnacles was producing dozens of earthquakes in a week, the rest of the system was strangely quiet. The Bay Area barely registered. Southern California produced almost nothing, and the truly dangerous stretches, the southern San Andreas, the reach out toward the Coachella Valley, have been assessed as sitting at extraordinary levels of stored stress. Parts of that southern fault haven't produced a major earthquake in something like 3.5 centuries. 340 years of silence on a fault that's being loaded at full plate rate every single day. Now put those two facts right next to each other. 59 earthquakes in 6 days on the creeping section is strain leaving the system, energy being released. 340 years of silence on the southern reach is strain entering the system every day with no release. The part of the San Andreas that shakes constantly is the part that can't really hurt you. The parts that could one day kill tens of thousands of people are the parts that don't shake at all. Seismicity is a measure of release, not a measure of danger. And the version of this story that treats a busy week at Pinnacles as a warning sign has the physics exactly, completely backwards. The quiet faults are the frightening ones. The noisy one is, in a strange way, doing its job. So what should we actually watch over the coming weeks? A few things, and all of them are answerable with public data. First, whether this patch delivers something a little larger, because its history does run up to around magnitude 5, and the sequence was still ticking along at a reduced rate. Whether that 3.94 was the peak or the warm-up can only be known by looking back once it's over, but the catalog will tell us within days. Second, the creep meter record. The most likely explanation for this whole thing is a shallow creep transient, a stretch of fault briefly sliding faster than its long-term average for days or weeks, loading the little stuck patches embedded within it and making them fail one after another. That would neatly explain the slow buildup, the spread along the fault, and the shallow depths all at once. And it's testable because this segment has been watched by creep meters for more than 30 years. If they recorded a creep event last week, the swarm has a tidy explanation. If they show nothing, then the more unsettling alternative, a locked patch hiding inside a creeping fault, keeping its own generational schedule, gets a little stronger. And third, direction. Whether this sequence stays put, dies out, or slowly walks down the fault toward Parkfield is the single most informative thing the next couple of weeks can show us. So let me bring us back to the question I asked at the start. Is the creeping section a wall? The honest answer, the one the scientists actually stand behind, is this. Right now, today, it is behaving like one. It's releasing its energy quietly. It isn't banking the strain a great earthquake needs, and this week's swarm is almost certainly harmless. But the phrase creeping section was never a law of nature. It was only ever a description of how 150 kilometers of the San Andreas happens to be behaving at this particular moment in geological time. And 4 meters of rock, pulled from a hole 3 kilometers deep at Parkfield, tell us plainly that it has behaved very differently before. The wall we've all been counting on isn't a permanent fixture of the Earth. It's a phase, and phases, given enough time, end. That's the real payoff here, and it's not a reason to be afraid tonight. It's a reason to respect the ground a little more, and to trust the people patiently reading its story out of the rock. The most important discoveries about this fault didn't come from panic. They came from someone drilling a hole and asking a better question. If this changed the way you think about the ground under California, or if you learned something you didn't expect, hit that like button. It genuinely helps the channel more than you'd think. And subscribe to W for weather so you're here when we follow what this swarm does next. And I still want to hear it, so tell me in the comments. Do you think the creeping section is a wall or a fuse that just hasn't been lit in our lifetimes? Take care of yourselves, keep looking down as well as up, and I'll see you on the next one.